and your face has never been to a Buc-ee's. Mission Impossible 6 is based off an observing run that he did while in grad school. Completely true.
I'm making that drink too long.
He has read every sci-fi book ever, and he knows that there is no limit to the number of books you can check out from the local library. No limit to content. He does not have a cat. He has surfed before, so that makes him really cool. And he can do the Macarena blindfolded.
Prove it!
Yeah, definitely. Without further ado, here's Andrew.
Okay, thank you very much. Those are nice facts. What I'm going to talk to you about tonight is the Gaia mission, or the Gaia Space Telescope. And so Sarah talked about kind of the archaeology, the archaeoastronomy, so basically previous astronomy. This is kind of the cutting edge astronomy that we're doing right now in the Milky Way and doing with stars. So before I talk about Gaia, I'm going to show you a movie, which I have the clip. Okay, it's going. So this is basically kind of a snapshot view of the Milky Way, starting from the very, very center and then going outwards. It starts kind of slow and then speeds up a lot, so this part, at least from my perspective, isn't exciting. But there's a supermassive black hole in the center. So this is about 1 light year across, and so you have stars orbiting the center. There's something there that they're orbiting around, but we can't see it, but we can see the stars. And then we're going to slowly zoom out. This will take a little bit. So you see more and more stars, and this will slowly grow to the galactic bulge in the center. And so in the center of the galaxy, there's a big spheroidal bulge. It's gonna. That's about where it is. And so this is the center. So it's about 10,000 light years across. And the next part is the stellar disk, which is a very thin disk. This is normally what you think of with galaxies, because this has the nice, pretty spiral arms and it's rotating. And also, with coincidence with this stellar disk is there's also a gaseous disk. This is mostly made up of hydrogen, neutral hydrogen, but it has some other trace elements associated with it. Then you have the globular clusters, which are large concentrations of stars. You have the stellar halo, which is kind of diffuse background of stars. Then you have the dark matter halo. And this is mostly the building blocks of the Milky Way. And this is kind of how we thought of the Milky Way kind of before Gaia. The last part of this is going to go to a sideways view so you can see the nice spiral arms. The one other thing I should mention is most of my videos and pictures came from the ESA website. So if you ever get bored and want to look at nice videos and pretty pictures, go check it out. Okay. So just some quick facts about Gaia. This is my only slide with words on it. So it was launched about 5 years ago. And first it had a kind of a commissioning phase where they made sure everything was working. And then since that period, it's been continuously scanning the sky and taking basically precise measurements of the position of every single star it could. And the goal of this mission is to measure the position of every kind of bright star. And so bright here is actually very faint, but trying to measure the positions of every star that's bright with quotes around it about 70 times. And later that seems like a lot of measurements, but later I'll show you why we actually need to do this. Also, the data was just recently released, so this has kind of been a flurry of learning about what's going on. And right now, it's measured the position for 1.7 billion stars. That's a humongous number. Also, it's only 1% of the stars in the Milky Way. So, large number, but not everything yet. And so this is the goal that was written on the Gaia website, basically, in their proposal to do this mission. This is what they set out to do, which is to investigate the origin and subsequent evolution of our galaxy, the Milky Way. And since it's our galaxy, it's capitalized, as opposed to all the other ones. Okay. So next we have a very pretty picture of the Milky Way, basically all the stars that Gaia has observed. So what this is an overview of basically the brightnesses of all the sources that Gaia has observed. And this is in galactic coordinates. So right here, this is the center of the Milky Way. It's the brightest point there. And then this plane here, this is the galactic disk. So this is where most of the stars are. And one thing you'll notice is that there's a lot of kind of dark areas going across the disk. And what that is that's interstellar dust in between basically us and the stars behind them. And because the dust is there, we're not able to see the stars behind them. So some other things to note, you may be able to see kind of tiny pinpricks. That's not dust on the screen, that's actually either globular clusters that are satellites to the Milky Way or other dwarf galaxies that are satellites here. So there's these small concentrations of stars that are orbiting around the Milky Way too. Down here, these are the kind of smudges of stars. This is the large and the small Magellan clouds. These are our biggest companions. The large Magellan cloud is about 5 to 10% of the Milky Way, so it's quite big. But it doesn't look very big here because of how far away it is. Okay, now I'm going to look at the same image again, but instead of looking at it in brightness, I'm going to look in terms of number density, so just how many stars there are in the image. And so we can flip back and forth between them. So you can see there's a lot of stars in the center here. And actually, the Magellanic clouds, they get brighter in terms of number density. But in terms of actual kind of brightness, they don't look like they're much just because of how far away they are. The other thing I want to look at right here, these two objects, they basically go away when you look at brightness. This one right here, this is the Andromeda Galaxy, M31. It's our nearest neighbor. It's a little bit bigger than the Milky Way, but it's kind of the traditional, if you see a picture of a spiral galaxy, it's probably M31. But it's a little bit bigger than the Milky Way, but because of how far it is, you generally can't see it. I don't know if you guys can see this, but there are kind of roundish kind of things in here, maybe kind of string-like. Those are actually artifacts from how Gaia scans the sky. And so they're not real, but they will go away with time as Gaia builds up its satellites. Okay, so that was pretty pictures. Now I'm going to tell you about the two main kind of measurements that Gaia is trying to do. The first one is called parallax. What we do is, the idea is to image the star twice, and image the star roughly 6 months apart. So you first image it, say in January, and then you wait 6 months and you image it in July. And the reason why you want to do this is that in that time the Earth moves to the other side of the sun, and if the star is close enough, you'll actually see the star move relative to all the other stars in the sky. And so this is kind of a cartoonish version of it. So if you look at it in January from here, it looks like it's way over here. Then when you look on the other side, in July, it looks like it's up here. And that angle that you measure is proportional to its distance. So if you measure a large angle, that means it's fairly close. But if you measure something that's very small, it means it's far away. And so Gaia is trying to make many, many measurements of each star so that it can figure out basically how far away it is. So next, I'm going to show you a picture of parallaxes that have been measured. So here you see basically the stars spinning around here. And this is basically, if you look at the star many times, basically observe it each day, if it's close enough, you'll see it go around like this. And you notice that every star is spinning here, so it's going to loop around again. And so this star is the closest one to it because it has the biggest angular spin, whereas this one over here, which looks brighter, has a very small angle, which means that it's further away. So from this measurement, we can figure out how far away a star is. Okay. The next thing that we want to measure is something called the proper motion. And so what this is actually the star moving in the sky. So normally you think of the stars as fixed. They may move a little bit in the night, but that's actually mostly due to the Earth rotating. What this is the stars should be moving throughout the galaxy, it has to rotate. And so you see the stars basically moving tangentially. Now this is a very small effect. So if you notice this one here, this is Bernard's star as the largest proper motion that we know of. And if you look at this, this is 20 years that it took to figure out, to see this motion relative to everything here. And then this, these two here, this is actually a binary system that's moving. So I have another video. This one you may not be able to see them moving because when I was staring on my computer screen super close, they're moving. But hopefully you can. So, okay, it's not very long. I guess you can see these ones moving up over here. But this is just an example of how each star moves kind of tangentially on the sky. So if you guys see one, point it out, because it's kind of hard to find them. Okay, I think it's in a loop, but I'm just going to move on. So in reality, I described two motions, but they actually happen simultaneously. So this is observations from actually the Gaia satellite's predecessor, the Hipparcos satellite. And so this is examples of 3 different stars. The dots here are the actual measurements, and then these kind of squiggly lines that are drawn to them, that's the best fit of how these stars are moving across the sky. And so you can kind of see, moving up like this, moving around like this, and then they're processing around that just due to kind of when we observe it, what time period that we observe it. So now I have a video of kind of parallax and proper motion put together. The one thing I will say is before I put this started is for the parallaxes, those were increased by a factor of 10,000, otherwise you would not have been able to see them. And the proper motions have been sped up by a factor of 1 trillion. And so this kind of represents like a time period of maybe a couple thousand years or several thousand years to see these stars move. So at this point, this is just the parallax of the stars, how they're moving in the sky. And in a second here, this will overlay the constellations, and you can kind of see how the constellations would move if the parallax was a much larger effect. So this is, constellations moving throughout the sky. The ones that don't move as much, those stars are further away from us. And then what's going to happen soon is that it's going to go to how they're moving in proper motion space, and you'll see all of a sudden they just fly apart from one another. And so this is what the constellations are going to look like in 5,000, 10,000 years or so. And at this point, the stars here are now having both effects, where it's both parallax and proper motion, but it's kind of hard to make out the parallax effect. You can see the stars moving, but it's kind of hard to see the little kind of squiggling across the sky. Okay, so that was kind of an overview of the measurements that Gaia makes. Now I want to talk to you about some of the science results and why we're doing this. So the first one that I want to mention is not related to the Milky Way, but is related to kind of cosmology. It's called the distance ladder. The idea here is that we measure the distances to stuff precisely, or as precisely as we can, so that we can figure out how things further away from us are. So at this point, I described to you parallax, which basically says how far away the distance, the nearby stars are. And that nearby used to be, this is maybe 50 parsecs. Now we can go out maybe 100 times further in space. And then we measure the proper motions, the parallaxes of variable stars, and then we use the properties of variable stars in distance galaxies to figure out how far away they are. So this is basically very important in terms of cosmology. The next thing I want to show you is how the stars in the sky are rotating. So once again, this is a galactocentric map. So this is the plane of the galaxy, and then this is going above or below the plane, and this is going along it. So this plot is in galactocentric coordinates. So this is basically the velocity going towards the center of the galaxy or away from the galaxy. And what's shown here is in blue the stars are coming towards us, and in red they're moving away from us. And so what this is just simply showing us that the Milky Way thin disk is rotating, where here the stars are moving away from us, over here they're moving towards us, and then this inversion point is actually due to the fact that we're observing this inside the Milky Way disk, and so the stars here are moving slower relative to us, and they're moving faster on the other side of the galactic center. Okay. The next thing I want to talk about is kinematic substructure in the local neighborhood. So this is defined as within 200 parsecs, which is about 650 light years. So this is very nearby. And so there's two velocity coordinates here. This is pointing towards the galactic center, and then this is in the direction of rotation. And the main thing I want you to take away from this figure is that it's not smooth. If it was smooth here, that means that it's a simple axisymmetric system. Whereas substructure happening, if you see substructure here, that's indicative of different effects. For example, spiral arms, satellite galaxies moving through the Milky Way, resonances due to the galactic bar. And so this picture has way more substructure than we expected. We expected to see something a little more smooth. And in fact, some of the substructures that we saw before and we thought we could explain, they're making us have to think a little bit harder. So there's there's an overdensity of stars here, whereas up here there's an underdensity and whatnot. So this is something cool that we found. The next thing is not kind of the Milky Way, it's a satellite of the Milky Way. So this is a zoomed in picture of the Large Magellanic Cloud. So this is once again in terms of Gaia brightness. And we can actually see it rotating even though it's very far away. Can you guys see that rotating? I see some people nodding. But this is super cool. It's very far away, but we're seeing basically our neighboring satellite galaxy rotating in the sky, which is kind of crazy to think about. And so this is another way of visualizing it. All these lines that you see here represent the direction of rotation that are overlaid on the surface brightness plot of this. The last thing I want to talk about is orbits of satellites. The lines that you see here, there are two colors. Blue is the globular clusters. It's 4 globular clusters, basically how they're orbiting around the Milky Way. And then in red here, there are 3 satellite galaxies that are orbiting around the Milky Way. And before this, we could make measurements of them, but they're much messier. And so now we can very precisely see how all our satellites are moving around us. And you can also see some of these red ones, they've only gone around the Milky Way once or twice. So they're very far out on very long orbits. Thank you. Questions?
So that picture you said you're expecting it to be more smooth. Is that because there's more, say, galaxies that have been combined together than?
So you're asking about why it's more substructured than we expected.
Yeah.
So.
Is that because of satellite galaxies?
So some of it could be due to basically other satellites that basically are, it's called accreted, basically they fall into the Milky Way and then basically, you can think of it, they get eaten by the Milky Way and make the Milky Way larger. So, yeah, so there's more around them, there's more that fell in than we thought there was.
How much more do you think?
So one of the big things is we're from the Gaia data, we think a satellite that was about the 1/20th the size of the Milky Way basically fell into the Milky Way maybe 5 years ago. And so there's multiple kind of lines of evidence in that case that have all pointed in the same direction. There's also, you see spiral structure imprints on there too.
On that rotation map that you had of what's moving towards us, away from us, I want to understand. So, is the galactic core moving opposite the rest of it, or is that just relative motion?
So it's just relative motion. So this is motion around the galactic center, but it hasn't been corrected for the motion on the Earth here. So this inflection point here is due to the fact that the sun is moving through the galaxy at about 200 kilometers per second, and so the stuff here is moving slower relative to us, and vice versa for the stuff outside it. So that's a good question. This is actually the one question I expected people to ask.
Yeah, you said on like one of the last slides, some of the red movements around the galaxy, that some of them indicated just 1 or 2 revolutions. Does that mean 1 or 2 revolutions forever? Like that they just started and it took that long for the whole cosmology?
Yeah, basically because of how far away they are, they've only been around basically the Milky Way a couple times. So the Magellanic Clouds are a little different. They're actually coming in for the first time. So they actually